All right. So for your reading so far in the book, we're through 1.7. Is that right? Okay. Um, so let's go ahead and for next class, let's finish off that chapter up through 1.12. The last several sections are fairly short, so that's not like more stuff than you've dealt with before. Make sure you do all the little practice um, things in there so we can start transitioning into actual language stuff. Middle of the week, I think we're going to be getting pretty close to that after today's lecture. So that should get us kind of on the same page. If not by today's lecture, certainly after Wednesdays. All right. So last class, just to review a little bit, we were talking about interpreted languages versus compiled languages. And remind me, what's a compiler?
From high level into low level.
Okay, so it's a program that converts a high-level language into a low-level language because human beings, we like programming with higher-level languages, and ultimately computers need machine language, so we need something to take us at least part of the way there, right? So we go from our high-level language down to a low-level language, and then we use another tool called an assembler that ultimately converts our assembly language into a low-level language with the help of something called a linker. So relatively unimportant for us at that level, but those are the kind of the pieces that go along the way there. And we talked about kind of interpreted languages being relatively slow versus compiled languages being relatively fast, and this being all very much a relative statement, given that computers are really, really fast to begin with. All right, so we talked about compilers. We talked about domain-specific versus general-purpose languages. Those are pretty self-explanatory. We talked about functional versus procedural versus object-oriented. Specifically, we talked about procedural versus object-oriented. We used an example of a telephone for that, right? And we talked about how a object-oriented version of a telephone looks like a telephone, where a procedural version of a telephone might look like a big pile of wires until further investigation, and we recognize that, oh, it actually is a phone. We just kind of see a whole bunch of stuff that we aren't used to seeing related to the phone. So at the end of the day, an object-oriented language is effectively a procedural language with one additional, I usually say it's like a Tupperware container, one additional level of organization that allows us to stuff details that we don't need to work with very often inside and only expose the public interfaces that we actually need to work with in our objects. And all of that comes down to an ultimate goal, where we went back here, talking about the goal of a programming language is to give a human being a tool that allows us to solve problems the way we already solve problems. All right, and we right near the end of class last time we talked about well, why didn't we just start off with object-oriented languages? Well, I mean, we can make the assumption that building a programming language is probably relatively difficult, right? And in the very early days of computing, we went before this, but let's just kind of start. Our little chart here starts with C, which is like 1968. So back then, the types of problems we were solving were far more trivial than the types of problems we're solving today, where a procedural language didn't really show up as a weakness to us back then. It did everything we needed it to do, and we were, as humans, able to solve problems the way we were used to solving problems. Only when we started wanting more from our languages, only when we started, adopting computers to do more things for us and started realizing that we could automate more things in our life, did we start asking for more from the computer, asking for more from the language, and that's when we started running into these situations where a procedural language was kind of showing some of its weaknesses, and that's where we introduced, what's usually considered a major new paradigm. That's this object-oriented language stuff, but the reality is it's not much more than an organizational container. All right, so let's not kind of overthink it. So what we want to talk about today is kind of the evolution of our native languages, and we're also going to talk about our web languages as well during this week. So we're going to end up with a kind of a chart showing a whole bunch of web languages on the left, a whole bunch of native languages on the right, and kind of getting a big picture idea of what the modern computer programming world kind of looks like. So we have a context with which to do our I guess do our beginning programming. Usually or historically, I've done the web languages first and then done the native languages. That's when we were using Java as our teaching language. Since we're using Python as our teaching language this time, I'm going to flip-flop it because Python is over on the web language side of things. Most of the web languages tend to be interpreted languages. So really, when we look at these, we're going to be looking at interpreted languages on the left and native languages on the right. Compiled languages on the right. That's what it's going to ultimately end up looking like. All right, so let's talk about the evolution of C first. Okay, so when we look at C, and again, just as a quick reminder, we talked about last time how human beings solve problems, right? Talked about memory, asking questions, and repetition. I made a statement that 100% of programming languages provide facilities for these three things. We have a way of representing memory, usually through variables. We have a way of asking questions, usually through conditionals. And I say an if statement because that's what C brings to the table, is if statements. So since most of our modern languages, both web and native, come from C, pretty much anytime we ask a question, it's going to be an if statement. And then repetition comes in the form of loops and procedure things. Okay. So when we look at the evolution of C, we're going to mostly be looking at it through the lens of variables, how it represents memory. All right. So we're going to say that C supported variables. So this is a single name with a single value. All right. So we can create a single memory location and put one value in there. All right. Now, having said that, do I have strongly typed and loosely typed in here somewhere at this point? Let's go ahead and throw it in real quick. There are two kinds of programming languages. We have loosely typed and we have strongly typed. You sure we didn't talk about this? Okay. So strongly typed and loosely typed languages. This has to do with when we create variables in the programming language, whether or not we define what kind of value needs to be stored in there. And to kind of bring this into a real world example, let's say that you want to store tax receipts at your house. So you go over to Target, you buy a Tupperware container, you write on a Sharpie on the side of it, tax receipts, and you throw all your tax receipts in there and you shove it under the bed. Okay. Then all of a sudden you decide, I'm not going to pay taxes anymore. I'm lazy. I'm not going to keep track of tax receipts. So I'd like to rather store shoes in this container. Well, in a strongly typed language, that is a language we've already written on the side of the container in a Sharpie that this guy is earmarked for tax receipts, we can't put shoes in there. Even though as humans, we know that shoes would technically fit in the box, we're not allowed to put them in there in a strongly typed language. In a loosely typed language, we'll just scribble out the tax receipts, write in shoes, and move on with life. So in a strongly typed language, if we want to store shoes, we need to go out to Target and buy a specific container and earmark it for holding shoes. And that's what it holds from that point forward. And if we decide to change that, well, we can't decide to change that in a strongly typed language. Loosely typed languages, we can change it whenever we want. So for humans, we typically live our lives in a loosely typed way, right? We repurpose things all the time. So which do you think is better, loosely typed or strongly typed?
Loosely seems a lot more open.
Okay, it does. It's definitely more open. That's probably why human beings do it. Is there any downside to lose track of stuff? Okay, so if we take the extreme example, we have two containers under the bed. One has tax receipts in it. That's where we keep our tax receipts. The other one is where we keep our rattlesnakes. All right, and they are dark containers. Okay, in a loosely typed language, we're not going to label them. We have to check. So you have to reach in and find out, is this tax receipts or are these the rattlesnakes?
Well, you hear the rap.
Okay, obviously it's an extreme example, but probably most of us don't want to hunt and peck to determine where the rattlesnakes are stored, right? You might also say if you're storing rattlesnakes under your bed, there might be some additional psychology type stuff that you might want to look into. But and yeah, I don't know. There's people with like Bengal tigers. They keep as pets and stuff.
You know what's more expensive than a tiger?
Huh?
You know what's more expensive than tigers?
Oh, there are probably a lot of things, but now.
The maintenance.
Oh, to keep track. Well, why do you know so much about keeping Bengal tigers?
Not much about him.
It's just like no reason. Yeah, I can. Didn't I think Mike Tyson used to have a tiger? I mean, they eat like 60 pounds of meat a day.
They're trying to maintain that for years and years.
Jeez. All right, so human beings tend towards a loosely typed life because we like to repurpose things and stuff like that, and we tend to use the see-through Tupperware containers so that you kind of can glance and see what's in there as opposed to wearing the blindfold and reaching in and maybe running into a rattlesnake. But the side effect of that, and you mentioned, is maybe we lose track of stuff or speed. You know, if something is loosely typed and we're looking for something, if you have a dresser of drawers and you know that something is in one of those drawers, you kind of have to search through the drawers until you find it. So we can say that loosely typed is relatively slow. Strongly typed is relatively fast. Okay, and I think what you'll find is there's some patterns we're going to notice here. We're going to find that most interpreted languages, which are already relatively slow, are also loosely typed languages. Okay, most compiled languages, which are already relatively fast, are also strongly typed languages. Okay, so when you hear of a language being one thing, you can start making some pretty good guesses that it might also fall into a couple of other categories. All right, now one is not necessarily better or worse than the other. But knowing whether a language is loosely typed or strongly typed does give us some information about how we might solve problems in that language. Okay, if we have a loosely typed language and we're done using a variable up here, we can reuse it down below to hold something else. Sometimes that makes sense, sometimes it doesn't, because that kind of lends you towards this idea. Usually when we start talking about variables next class or on Friday, you know, one of the rules of thumb is you want variables to have reasonable names. So the variable should have a name associated with that's kind of indicative of what it's built to store. Well, if you're storing socks in a variable, you might have a variable called my socks. All right. And then if you decide that you're going to start putting tax receipts inside of the bucket that used to be for holding socks, now all of a sudden you have a variable called my socks that happens to hold tax receipts. It's a little bit misleading, right? So, yeah, well, yeah. That's I always very clearly label my rattlesnake box. Yeah, I would suggest you do the same, to be honest. Okay, so, you know, the punchline is even though we could repurpose the variable, because of naming convention stuff, it's maybe not that great of an idea. Because when you have a variable, especially when you have, hundreds of lines of code, you might want to rely that the name of this variable gives you a pretty good indication what it's holding, right? So even though you could repurpose it, you might go ahead and create another variable anyway so that it has a name that indicates what's actually in there, okay? Because having a variable called my socks that holds tax receipts is somewhat misleading, even though it technically would be allowed in a loosely typed world. Go ahead.
Just out of curiosity, what is Java?
What is Java?
Yeah, basically your strongly typed.
Yeah. Oh, well, Java is a strongly typed language. So Java is like a piled language that's strongly typed, that's object-oriented, that's general purpose, that's high level. So that's where Java fits. On the flip side, Python is high level, loosely typed, interpreted, general purpose, and pretty object-oriented. It's kind of was originally procedural and then became object-oriented, that type of thing. And we're going to cover each of those languages in more detail as we talk about the evolution of these languages here. So evolution of C, we have variables, a single name with a single value. We also have something called an array, which is a single name which holds a collection of like values. All right. We also have something called a struct, which is a single name which holds a collection of potentially unlike values. I will say that's good right there. Okay, so in the early days, we're calling this the early days, in the late 1960s, so kind of from a modern computing standpoint, when we're writing our software, the types of problems we solved back then, we look at a language like C, which was originally built for writing operating systems. So it was originally built for a problem that was considered to be relatively complex. Even by today's standards, operating systems are difficult. They're complex software applications. But we could also make the assumption that our operating systems today are probably far more complex than our operating systems were in 1968, right? Okay. So this language came out and it fulfilled its purpose. It did all of these things. So if you needed to hold some socks, you could create a variable and put socks in there. You know, if we're taking this back to the computer world, if you needed to hold an integer, you would create a variable capable of holding an integer and you would put an integer in there, put a number in there. If you needed to hold a whole bunch of integers, you could create a single variable that created containers to hold a whole bunch of integers. And those things were called arrays, a whole bunch of similar values, like values. Now, what if you wanted to hold things like a first name, a last name, and an age? So 3 pieces of information about a person. Well, C had something called a struct, a structure. And a struct would let you define something like called a person and say, this guy's allowed to hold a string, another string, and an integer. So we can hold a single name, person, underneath, and inside it can hold a collection of not necessarily the same kinds of values. So we can be a little bit, I guess more discrete. So for example, in a language like C, we could create a struct called person, and we could say a person held a first name, a last name, and an age. And then we could say person P dot first name is equal to Mike, P dot last name is equal to Whitman, P dot age is equal to 21. All right, so C would let you do things like that. Now, if you then wanted to display information about this person, so we go way back to when I said how do human beings solve problems. We talked about repetition, and the mapping was we do things through loops or procedures and functions. So chunks of code that can do things, we write it once, they do things multiple times. So we might want to have a procedure that we could pass a person to, and it knows how to display that person's first name, last name, and age, for example. All right. So if we're in C and I want to have the ability to display information about a person, I might have a function called display, takes a person as a parameter, and this guy maybe does and don't worry about this too much. I'm actually writing it in C-style syntax just so we can kind of see how the language has evolved. So this would be P dot first name, P dot last name, P dot age.
What language is this?
This is C. You don't have to memorize this or anything. I'm just kind of giving you some visuals for how these languages evolved. All right, so we created this structure for holding information about a person. We went ahead and we created one of these persons. I named this guy P. I could create a second person named P2 that is equal to another person, another first name, another last name, another age. I can then say something like, display P. So I can pass this person into this function, and whatever this person is, it would print out that person's first name, last name, and age. So this would say Mike Littman and a little dash after it, then 21 for age. Okay? Now, and then if I wanted to create a second person, I could pass it P2. So I would say, if I copied these lines right there and I created person P2, and maybe it was my brother David Littman, and put an age in there, I could call then display P, and then I could call display P2. So I'm using the same display method, the same procedure here twice to print out information about two separate persons, okay, because it took in a generic person as a parameter. So a language like C lets you do stuff like this. But a weakness of this is we might, in real life, decide that when we start building objects, that a person might be able to report their name. They might be able to report information about themselves. So if I went to any of you and I said, tell me about yourself, display yourself, every single one of you would be able to say, oh, well, my first name is this, my last name is this, and here's my age, right? You wouldn't have to walk into some booth over there to have somebody convert you into those pieces of information. Like plug you in and yank those pieces of information out, and then it shows up on a little output because you couldn't do it yourself. So when we think about human beings, we think about them being more than that, just these empty husks that walk around, right? Okay, you have these attributes associated with you, but you're also able to report on those attributes. We think of the world like that in terms of objects. Well, in the early days of computing, even though this seems to be obvious to us right now, the types of problems we were solving in the very early days didn't even go this deep. We were doing a whole lot of little mathy stuff, adding stuff, subtracting stuff, doing a lot of accounting type problems, okay? Not really dealing with personal type applications or information, records of people and that kind of stuff. All right, so in the ideal world, we would be able to take that function and suck it into the struct itself. Have that become something that the struct has built into it. Just like we would say in the ideal world, every human being would be able to report their name and their age without needing some helper to pull that off. That makes sense? So in one of our early languages, like C, early-ish language, it wasn't anywhere near the first programming language, okay, but we're going to say it's one of the early languages that we care about as modern programmers, we could not pull that off. And as programs got more and more advanced that still use C, in fact, C is still around today. Okay, it's not that people don't use C at all today. C++ is probably more common in jobs and stuff today, but C is still around. Towards the end, we started having this little hack. So what would end up happening is inside of our structs, we would create a variable that was of type void pointer, and we might call this proc pointer or something like that, and we would somehow get this guy to link to the memory address where this function actually lived. So we started looking for workarounds, how we can sort of kind of make a person struct do sort of kind of what we want it to do. Okay, but it wasn't something the language was built to do on its own. It was something that, as programmers, we kind of found workarounds to get it to act a little bit more like we want it to work. Which then leads us to look at, okay, well, maybe we need a new programming language that at least upgrades the existing language to have a couple of facilities in it to make our lives easier. Make sense? So what did we do? Well, we'll talk about the evolution of C++. Kept the variables, kept the arrays, kept the structs. But we added a new thing, the piece of Tupperware. This is a single name which holds a collection of potentially unlike values as well as functions slash procedures. Maybe a little bit more than that, but that's good enough for this top level, high level explanation. All right, so just like our example from last time where we talked about the procedural telephone versus the object-oriented telephone, this language allowed us to do the object-oriented telephone. It gave us this new piece of Tupperware that could encapsulate both the wires, the detail wires, and then punch holes through it so we could actually have the public pieces of the telephone that we'd actually use. All right, so this gave us that one more organizational piece. At the end of the day, the biggest difference between C and C++ was just that, this one thing called a class. Make sense? So if we're talking about weaknesses here, we might say a weakness of C, so when I say problem. As programs became more complex, the language started showing organizational weaknesses, something along those lines. All right, now, as you might imagine, this little picture here doesn't stop at C++. We have even more modern languages. So, what was the problem with C++? Anybody know? Who hasn't had my class before? C++ is still used relatively heavily today, especially in video games. But C++ does have a major problem. Okay, so we're going to say problem. Empowered the programmer to make bad choices. Okay. Really, the biggest issue for C++ was for people using that language as their learning language. C++ allowed you to do things, potentially by mistake, that were not very wise things to do. The example I like to make from real life is, let's say you're having a party at your place. All right, you're gonna invite me to the party. And let's say the party's tonight at 8 o'clock. Do you give me the address to where your house is, or do you hand me the house and tell me to open the door at 8? Give me the address. Would it ever make sense for you to actually hand me your house?
No.
In real life? Why?
I gotta give them where I live or something.
Houses are heavy, for starters, right? Okay. We can't lift houses. Even a little tiny house, isn't that the new trend, the tiny homes? You seen the TV show? Even those are heavy, right? Plus, you have the problem, what if you have more than one person you're inviting to your party? Well, now you have the problem of, what do you got to kind of start stacking them on the porch and carry the house around, kind of, pizza style? Just keep going around and stacking more people on your porch. We want to be able to hand you the address to the house, you the address to the house, you the address to the house, and have us all come together at 8 p.m. at the one central house, right? So in real life, it would never make sense for you to hand somebody the house and tell them to open the door at 8. In a language like C++, the programmer could choose to do that. Now, having said that, do you imagine that in programming, every now and then, that might be what you actually do want to do? Just because we're saying it would never make sense in real life. The argument I typically make is that in computer programming, about 85% of the time, it mimics the way we solve problems in real life. Okay? But the main reason why we wouldn't give somebody the house is because it's heavy in real life. It's just not practical. But every now and then, it might be handy for you to hand somebody the actual house in this example, for whatever reason. One thing that programming does let us do is it does let us cheat reality a little bit. Every now and then, if the particular nature of the problem we're trying to solve happens to dictate it, we can do something that we wouldn't otherwise do in reality. All right? So that's one thing we might say is nice about C++. It gave us that flexibility. But now if you're a beginning programmer and you don't really know any better, so for most of you, when you start writing our Python code, you've already started a little bit in the book. And the last 4 sections has you write some more code on your own. And then we'll start transitioning into kind of learning the language at a higher level. But you're probably already noticing some patterns. You're forgetting one of the things the book is drilling you on is the opening and closing quotation marks, or making sure you have the closing parentheses. What's a variable versus what's a string? Little tiny little details that you have to make sure you don't forget. I don't know if I don't remember which section it's in, but there's one section that has, a bunch of, is this line an error or not an error? And it shows you a line of code, and at a glance, it looks correct. But I think half of them, or more than half of them, there's something tiny wrong with it. So it's kind of drilling you on the attention to detail you need to pay to those things, because when human beings talk to each other, if we forget to use the plural of something, or we use an adjective incorrectly or something like that, a human being can usually fill in the blanks or get the gist of what you're talking about, right? That's something we can usually pull off as people. Our interpreters and our compilers, that won't work. Okay, so we need to be very explicit. So we're going to have to train ourselves to be, really anal about the code we write, and that's kind of what the book's having you start to practice. Well, one thing you're going to run into, and I'm assuming from some of the code you've already written in the book, I'm not sure which section have you already started writing a couple of lines of code? Okay. One of the things that you've probably run into, at least some of you, is it might take you 2 or 3 tries until you finally get it right. Okay? Because you're leaving something stupid off, or like, oh, why didn't I do that? Or kind of the confusion between a string or a variable, whatever it is. As a beginning programmer, you're going to be significantly more prone to make mistakes. That's okay. You're supposed to. Okay, we're practicing. When you first start learning how to ride a bike, you fall off pretty often, right? I made the mistake of taking the training wheels off my bike way before I learned how to ride a bike, because I was a stubborn kid. So then I couldn't ride. Hey, is that normal, or do the parents usually take the training? Do training wheels still exist anymore? We still use those, don't we?
They have these, they're like really small 2-wheel bikes, but they don't have pedals, so the kid just push.
Oh, okay.
And then I think it has like little stands you put your feet on, so you coast.
I see.
It might be their way of transitioning out of using that.
Oh, I got you.
Right onto a 2-wheel.
Yeah, I just decided to take the training wheels off my bike, but I was nowhere near ready for training wheels to come off the bike. Yeah, so I don't remember how that all. Eventually, I did learn how to ride a bike. I'm pretty sure. But in any case, when you're a beginning programmer, you're going to be prone for errors. Prepare for it. You're going to make stupid mistakes. And later on, you're going to laugh at it. You're going to say, "Well, man, I can't believe I used to do that," but you will. Okay, it's normal. So C++ and similarly C are kind of dangerous languages to use as your beginning programming language, because they're almost too powerful for their own good. They give you a lot of flexibility. Both of these languages have built into it something called a pointer. Anybody know what pointers are? Okay, tell me about pointers.
Pointers are simply something which points to the address of a value in memory.
Okay.
So, like the store variable tells you where that variable is.
So it's a variable that's capable of holding a memory address. No different than us saying something else is a variable capable of holding a number, or it's a variable capable of holding a character. They're all the same thing. But now one thing happens with people. Which of these 2 values is scarier to you? The number 5 or that? You run into either of those in a dark alley. Which one do you run away from first? Second one looks scarier, right? First one, we deal with numbers all the time. We recognize the 5. Okay? kind of like you're in the alley and you see a squirrel on the fence, you don't freak out. Okay? Now, you see a Bengal tiger in the alley,
You panic.
you panic, right? You panic. So this guy's the Bengal tiger. This guy is the squirrel. Little do you know that this is a squirrel with a really bad attitude, and this Bengal tiger has actually been raised since birth in an orphanage or something. So it's actually quite tame, right? But the point, that's right. The point is, at a glance, memory address looking things are intimidating. Okay. Especially when you're a beginning programmer, you're not used to dealing with these things, and as soon as things stop looking kind of English-like or comfortable for humans, we get intimidated, we freak out. So memory addresses aren't the way you really want to start with computers. When we started talking about our languages last week, we were talking about that we really steer clear of the zeros and ones, and there's really two reasons for that, right? One is it's not really compatible with us. We wouldn't do well with the 2-button keyboard, things like that. But at the same time, if a computer program just looked like a giant wall of zeros and ones, that's going to be kind of intimidating. You're going to be like, well, A, I'm not capable of handling that. B, maybe this isn't the right career path for me. All sorts of things. That doesn't seem fun. That seems like it's too much work or just not really compatible with people. So memory addresses, while maybe not that bad, and in reality, they aren't all that bad. Okay. At first glance, they do become intimidating because we actually deal with addresses all the time, but we don't think anything of them. So everybody in here, if you're buying something from Amazon, you can put your address in, right? And you don't start getting scared when somebody asks you for your street address or something, because it's something that we're used to dealing with. Memory addresses in the computer are the same thing. They just look scary. This isn't as easily as 123 Main Street, right? Even though from a computer's perspective, it's the same thing. Okay? In fact, memory inside of a computer is actually easier than real life memory. Okay, so if you were a pizza delivery person in a computer, all the houses are on one street. Just depends on how many houses down do you go to deliver the pizza. So at the end of the day, this scary looking number, this is a hexadecimal representation of a number. Okay, this might be house. Well, I don't really want to do the conversion for this, but this is the ones place, the 16s. I don't want to do the conversion. Giant number. Okay, so let's say this is the house number 6,294. It's actually bigger than that, but let's just say that's what it is. So I'm going to go down roughly 7,000 houses until I finally get to the house I'm supposed to deliver the pizza to. That's how computers work. You just have one gigantic street with the houses numbered one after another. Pretty easy, right? Now, it just so happens the world doesn't quite organize like that. We're not just one big straight line. We have a whole bunch of streets within a certain zip code, and you have streets that share the same name across zip codes and all this stuff. So our addresses in real life are actually far more complex than these are. But we're used to them. We've been dealing with addresses for our entire lives. We're comfortable with them. These guys look scary. So the second we start dealing directly with memory and computer programming, especially when we're beginning programmers and we have enough other things to worry about, we get out of our comfort zone and it starts becoming problematic for us. So as a beginning programmer, to have to deal with memory at any level is one extra thing that maybe we don't need hanging over our head. All right? And to make things worse, languages like C and C++ give us special syntaxes. So, for example, let me actually put this on a different slide just so I can give you the example here and it all fit. So this slide pertains to both C and C++. So let's say I define, these are both strongly typed languages. So I'm going to go ahead and I'm going to define an integer called A, and I'm going to set it equal to 5. Okay. Then I'm going to create an integer pointer called B. I'm going to set this guy equal to the address of A. Then I'm going to print out A. Then I'm going to print out B. When I print out A, it's going to print out the number 5. When I print out B, B holds the value of the address of A. So this is going to print out scary memory address. So prints 5, prints mem address. Print address A will print out the same thing as just printing out B. So this prints memory address. Printing star B will print, whatever, 5. So we have this special syntax dealing with asterisks and ampersands that allow us to dictate whether we mean the memory or whether we mean the value at a memory location. That makes sense? Gets even worse than that. We can have double pointers. We can have a pointer to a value. Sometimes that makes sense. So if we have a pointer to a value, we can have something like int pointer pointer C is equal to the address of B. So C actually holds the address where the variable B lives. And the variable B happens to hold the address of where the variable A lives. And the variable A actually holds the value 5.
I got it.
All right, so with that in mind, we can come down here and we can say, well, I can print out C, which will print a memory address. I can print out star C, which still prints a memory address, just a different memory address. This one happens to print the memory address that's stored inside of B. I can print out star star C, and this guy will print out 5. And you can just keep going from there. You can have pointers to pointers to pointers to pointers to pointers. Punchline is there's enough extra complexity here with C and C++ that this can get overwhelming pretty quickly. The reality is you don't have to use pointers, especially when you're a beginning programmer. You might not run into too many situations where a memory address is absolutely required. But, and we'll learn it in here, sometimes knowing that something is living on a memory address versus something as a copy of something on a memory address makes a difference to us. But we don't need to deal with that day one. This was even a bigger problem in the early days. So if you wrote a computer program that started manipulating memory in C or C++, and you happen to overwrite part of your system memory where the operating system lives, your machine might crash, and then you have to reboot your computer, boot back into Windows or whatever in order for you to keep doing your homework. Start over. So now at any point in time, you might crash your computer because you're screwing around with memory. Now, modern computers, like if you're a C++ programmer today and you're using like Microsoft's tool, Visual Studio, Visual C++, they have protections in place that, they kind of protect you from yourself. So if you start going south with memory, you're only working in kind of a protected memory space, so you probably won't crash your computer and then have to reboot. But the punchline still is that you can get into trouble working with memory. And we looked at that as a weakness of C++, let's say most of the time. Every now and then, we want to directly manipulate memory. But a majority of the time, there was only one right way of doing something. Yet C++ empowered you to make some wrong decisions that weren't memory efficient or things like that. So this is where the evolution of Java came from. All right, so let's get this guy on our so there's Java, 1994-ish, I think is when Java came out. ballparky. It's within a couple of years. I think we're pretty close there. All right, so Java came out there, and when we talk about the evolution of Java, we have variables, we have arrays. They got rid of structs because what the Java people said, incorrectly I might add, is that, you know what? A couple minutes ago when we talked about, structs weren't enough, we said that, as a C programmer, I build a struct for a person, but all a struct can do is hold the high-level attributes, name, age, phone number, stuff like that. They couldn't do things, right? So that's where classes came in, where we could bring those procedures into our structs so that a struct can do more than just store attributed values. It could also do some stuff, all right? So the Java people argued, you know what? A class that you choose not to implement methods in is actually a struct. Okay, so in C++, if we go back to this guy right here, I'm going to copy this. We'll paste it here. If I change the name here to class person, the lowercase c, this is allowed in C++. I can choose to create a person that holds some pieces of information and not actually put any methods in there. I didn't have to put procedures or functions or any of those things in there. At that point in time, logic would say, I might as well have just created a struct. They seem identical. Does that seem reasonable? So Java said, well, why should we support structs where if you need the functionality of a struct, you would just create a class and choose not to put any methods in there. There you have a struct, effectively a struct. There's one side effect to that though, and it's something that we were kind of talking about here with pointers and seeing with our whole situation here. C++ empowered a programmer to make bad choices, but things did happen in a default way. So we have this concept called variable passing. We can pass by value, or we can pass by address. All right. So we already talked about an example of pass by address. If you're having a party, you would hand people the address to your house. The house exists once. 20 people all have the address. They all come to that one place, right? If I gave any of you the address to my house and you went to my house after class and you spray painted the garage door, when I come home, I'm going to be in for a surprise, right? You didn't spray paint a copy of my house. You spray painted the actual house, okay? Because I gave you the address to where the physical actual house lives. Now, with that in mind, let's say I had a couple of quarters in my pocket, and I hand you a quarter, and you spray paint that quarter, you bend that quarter. Did that have any impact on the other quarter in my pocket? No, you were working with a copy of the quarter, right? I didn't put you on some wild goose chase of where you could find a quarter. I gave you a quarter by value. Okay, giving something by value is a copy of the variable is passed. Okay, it's a whole separate copy. It's not linked to the original at all. They just look the same. Make sense? Pass by address is the address to the single value is passed. This is me telling you where my house is, giving the address to my house. So when you go and spray paint the door, I find out about it later. Make sense? So pass by address, pass by value. One is not necessarily better or worse than the other. They're just different and they do have a side effect. So for instance, this guy here, we say no side effect. You bend that quarter, it did not have any impact on the other quarter in my pocket. There was no side effect because you were working with a copy. This guy has side effect. Spray paint the door at my house, I'll find out about it, right? Okay, that has side effect. So just in our last minute here, the punchline comes down to how things happen by default. Starting back with C and then C++ kept this as a standard, structs are passed by value. A copy of the struct is sent. Objects, classes, starting in C++, are passed by address. So the reality is in Java, if I have a class that I choose not to put methods in, so it acts like a struct, it doesn't quite act exactly like a traditional struct. Because if I pass that class to a procedure, it gets passed by address as opposed to the default for structs, which was by value. So it didn't behave identically. Now, most of the time, this might not have made any difference. But if somebody tried to change that struct inside of the thing you passed it to, that change would have global side effect as opposed to them working with a copy as they could have traditionally relied upon. All right, so Java kept variables, kept arrays, dumped structs, got rid of classes. So let's start next time talking about JVM Java stuff. All right, so homework, finish reading chapter 1 in the book and do all the exercises. Again, thread of the quiz is there. I will see everybody on Wednesday.